We will discuss some examples concerning the thermal cycles and how to solve a given thermal cycle. The first example we have is 9 moles of a diatomic gas. Diatomic means you know the F, the degrees of freedom, CV equals 5R over 2, CP equals 7R over 2, and the gamma is the ratio between CP and CV. So Cp over Cv is 7 over 5, which is 1.4 for the diatomic gas. The shown cycle is constant pressure process from A to B, constant volume process from B to C, and an adiabatic process from C to A. Now we have this reversible cycle. The temperature at A is 300 Kelvin and the temperature at B is 600 Kelvin. It's also given the volume at point B and C. The first required is the pressure at point A. If we will use the pressure at point A, we want to get it using the state function. But in the state function, we know the temperature, but we don't know the volume. The volume at A is unknown. So I cannot get it from point A. But if you examine the point B is the same pressure, but we have its volume is 0.2, and we also have its temperature. So we know two state parameters, temperature and volume, we can get the pressure. At state B, PV equals nRT. So P equals nRT over V, put N equals 9, R 8.314, the universal gas constant, and the temperature at B is 600. Divide by the volume. When you divide by the volume, you get the pressure in Pascal. This pressure at B, it is the same as the pressure at A. We don't have enough givens at A to calculate the pressure from this state. So instead, we calculated the pressure at B, which is the same pressure. After this, we want to get the volume at A. Notice that from A to B, this is constant pressure process. In constant pressure process, the volume is proportional to the temperature. You notice that the temperature is double from A to B. So also the volume is doubled from A to B. So the volume at A is half the volume at B. We can get it 0.1 meter cube. VA over VB equals TA over TB. 300 over 600 is half. You can get volume at A, which is 0.1 meter cube. Now we want to calculate temperature at point C. If we want to apply the state equation at point C, we don't have the pressure, but we have the volume. This is not enough to substitute in the state equation. That's why we will use the relation of the adiabatic process. In any adiabatic process, the temperature and volume are related between the states of the beginning and the final of the process. In the adiabatic process, Tv to the power gamma minus 1 is constant. Tv to the power gamma minus 1 is constant. Now we want to get the temperature at C, and we have the volume at C. And in A, we have the temperature and the volume because we got this volume 0.1 meter cube. So apply the relation Tv to the power gamma minus 1 is constant. From C to A, apply it at point C and equate it at point A. What is the unknown here? The unknown is the temperature at C. So one equation in one unknown, get the temperature at C. And of course, after substituting, it is in Kelvin. Now we want to calculate the last required, which is the efficiency of the cycle. To calculate the efficiency of the cycle, we want to substitute in the equation of the efficiency, which is 1 minus QL over QH. I have to find all the heat energy and get QL, which is the amount of heat energy rejected, and get the amount of QH with the amount of heat energy absorbed. We have only three processes. Process from A to B, then from B to C, then C to A. Let's calculate the heat energy. I will calculate QAB, QBC, then QCA. After calculating each heat energy, each Q, I can get QH and QL. In the first process from A to B, it is constant pressure, so QAB equals NCP delta TAB. N is 9 moles and the CP is 7R over 2, and TA minus TB is 600 minus 300. You always take the final temperature minus the initial temperature. So the final temperature is 600. The initial is 300. This is the delta T. After substituting, we can get Q in terms of R. Then we will calculate Q from B to C. The process from B to C is constant volume. So the heat energy could be calculated NCV delta T. Now you will put the number of moles and use CV, which is 5R over 2 for a diatomic gas. Then temperature of C minus temperature of, we have already calculated temperature of C, subtract temperature of B. Now you have this Q is negative, which means we are losing, or the gas is losing, heat energy. As for the third process, it's an adiabatic process and no heat exchange in the adiabatic process, so Q equals 0. This is QL, or QL is the amount of this value, the value of this without the negative sign, and this is QH, which is heat energy absorbed because it's the positive part. We can substitute to get the efficiency, which is 0.1127, and in percentage is 11.27%. This is how you solve the efficiency of a cycle. We'll take another example on a reversible cycle as shown in the figure. This cycle is a triatomic perfect gas going through the shown reversible cycle. Triatomic means that F is 6 and CV 3R, CP is 4R. Let's notice what we have in the thermal processes from the PV diagram. From A to B, this is constant pressure process. From B to C, this is constant volume process, like the other example. Then we have CD isothermal. Take care, it's written here isothermal. It's not adiabatic like the last example. Then we have a fourth thermal process from D to A. So now we have 4 processes consisting this cycle. And all the values of pressure and volume are given on the figure, and also it's given the temperature at A and the temperature at B and the temperature at C. What is required? The first required is to get the number of moles, heat rejected through the cycle, and heat absorbed. Heat rejected is QL, heat absorbed is QH, which is the amount of heat absorbed is positive. The amount of all the heat rejected, we add all the negative and remove the negative to take it magnitude. Then you calculate the efficiency of the cycle. Let's start. To find N, the number of moles, we need to substitute in the equation of states. But choose which point to choose. Choose the point which have all the state parameters given. Notice that at point A, we have the pressure and we have the volume and also the temperature. And the same at B and the same at C. You can use any of these states to calculate the number of moles. So I will choose the state number A. State number A, PV equals nRT, N equals PV over RT. The pressure at A is 2, but 2 atmosphere. When calculating here, I take it 2 to the multiplied by 10 to the power 5 to convert from atmosphere to Pascal. Multiplied by the volume, which is 4 liters. Also, we are not using liters, we are using meter cube, so you will multiply by 10 to the power negative 3. Then divide by RT, R 8.314, and T is 3 Kelvin as given in the figure. Substitute to get the number of moles. Now we want to get QL and QH. So we will make 4 steps. We will calculate QAB, QBC, QCD, QDA, and then check which of them are positive and which of them are negative. When calculating QAB, AB is a constant pressure process, so QAB is NCP delta T. When calculating QBC, it's NCV delta T. As for the isothermal process, the Q is nRT ln V final over V initial. So from C to D, it's nRT ln VD over VC. And for the last process, it is again constant volume process, so it's NCV delta T. After substituting with all the temperature, you will calculate QAB, you will find it positive. And BC, you will find it negative. And CD, negative. DA is positive. The sum of all the positive heat energies is called QH. So you add 192R plus 48R to get the total amount of heat energy absorbed. This is QH. As for the negative heat energy, negative means heat energy is rejected or repelled by the gas. So I will add these two, but QL is the amount of or the magnitude of heat energy rejected. So I will not take the negative sign. I will remove the negative sign. This is how you can calculate QL and QH. Then simply you will substitute in the equation of efficiency 1 minus QL over QH, which you will get 6.4. Another example on the cycles, we have a perfect gas. Perfect means ideal gas through a circular cycle as shown in the TS diagram. Take care, this is the TS diagram, not the PV diagram. The maximum temperature is 600. It's given that the maximum temperature is 600 and the minimum temperature is 300. These are the two givens. It's required to find the total work and the efficiency of the cycle. Let's examine this figure. This is a TS diagram and it is kind of a circle. This value is 600 and this value is 300. If you want to get the radius of this circle, the diameter will be 600 minus 300 is 300. And its radius is 150. 150. And this point in the middle of 300 and 600 is 450 Kelvin. And of course, this is the entropy on the x-axis. Now I want to find the total work. How to find the total work? We know that in the TS diagram, the area enclosed by the cycle is the amount of heat of the cycle. So the area enclosed in the TS is the Q of the cycle. But it is the same as the work because in the cycles we don't have change in internal energy, so Q equals W. So all I have to do is to get this area. To get this area, this is the area of a circle, which could be calculated by pi r squared. That's why we calculated the radius of the circle, and then you substitute with the value to get the amount of heat and the amount of work done per cycle in joules. The second required is the efficiency. To calculate the efficiency, we want to have work and QH. We already calculated the work. Now we will calculate the QH. What is the QH? It's the amount of heat absorbed during the cycle. The gas absorbs heat when the gas is expanding. The gas is expanding, increasing in volume during the path A, B, C. Then the gas is contracting, decreasing in volume from C, D, A. I want to calculate only the amount of heat the gas is taking during the path A, B, C. To get the amount of heat, it is the area under the curve. So I will take only half the circle and get all the area under it. Half the circle and get all this area. So QH is the area under the ABC path only because during ABC, volume is increasing. Then pi r squared over 2 plus 450 multiply 300. This is the area of the circle divided by 2 to take only half the area of the circle. And then you add the area of the rectangle. This point is 450 and this width is 300 because it's the same diameter of the circle. Now you have QH and work. You can substitute in the efficiency equation to get the efficiency of the cycle. An example on heat engines in nuclear power station produce steam at 500 Celsius and converts it to electrical power of 155 megawatt. What is mentioned in this example is the output power. The power is calculated in watt, not in joules, because power is the rate of change of energy. So it's energy divided by time. Watt is joule per second. So take care if in the problem you are dealing with power, you are not dealing with energy. It's energy divided by time. If the temperature of the steam is reduced to 50 degrees and the station works with Carnot efficiency, find the rate of heat lost per second. To solve this problem, we will draw the sketch of the heat engine. We are used to draw a circle representing the engine. This engine is absorbing QH and rejecting QL to the low temperature reservoir. Instead of dealing with QH and QL, we will deal with QL dot and QH dot, which means power, not energy, because the output now is power, not work. This is the output power, which is given 155 megawatt. This engine is working as a Carnot engine, so the efficiency of Carnot is 1 minus TL over TA. It's stated in the example that TH is 500 Celsius and the TL is 50 Celsius. But we are not substituting with TH and TL with the Celsius. Instead, we will use the Kelvin as we discussed before. So eta of this engine is 1 minus 323 over 773, which is 0.58. This is the eta of the engine. From other view, the efficiency of the engine is work divided by the heat absorbed. Instead of writing work divided by the heat absorbed, we will write it dot rate of work and rate of heat absorbed. So this is power over QH dot. QH dot equals power over eta, and you can get the QH dot. This is the rate of heat energy gained per second. But what is required is the rate of heat energy lost per second. So I want to calculate QN. Okay, the power is the difference between QH dot minus QL dot. So QL dot equals QH dot minus P. Now we can calculate QL dot. Another example, it's a Carnot cycle working between TH and TL, and its efficiency is eta naught. If the hot temperature reservoir temperature is doubled to 2H, so we will double the hot temperature. We want to calculate the new efficiency of the engine. From case 1, eta naught equals 1 minus QL over QH, but it is Carnot cycle. So we can use TL over TH. So eta naught equals 1 minus TL over TH. I will get the value of TL over TH in the left hand side. It is equal to 1 minus eta naught. The other engine is working at 2 TH. So the new efficiency will be 1 minus TL over 2 CH. Now it is double. But we know from the first case the value of TL over TH, which is 1 minus eta naught. Substitute, you have half and 1 minus eta naught. You will get the relation between eta dash and eta. Eta dash equals 1 minus half, open bracket, 1 minus mu, 1 minus eta naught instead of TL over TH. Multiply the half in the bracket, so 1 minus half plus eta naught over 2, and you will get the relation between eta dash and eta naught. Another example, using a refrigerator, a vessel containing 5 kilograms of water at 10 degrees is put into a refrigerator. The 1 over 7 horsepower motor runs for 5 minutes just to cool the liquid. The horsepower is a unit of power, and the power is joule per second. So we have the power given to the compressor of the refrigerator, which is 1 over 7 horsepower. 1 over 7 horsepower, to convert it to watt, we multiply by 746. 1 horsepower equals 746 watt. Just to cool the liquid to the refrigerator's temperature of 0 degree. So we have water cooling down from 10 degrees Celsius to 0 degrees Celsius when we put it in the refrigerator. So this refrigerator is absorbing or taking heat from water. This is the amount of QL. This QL is the same amount the water loses as it cools down from 10 to 0 degrees. First step, the work equals power multiply time. So it is 1 over 7 horsepower multiply 746 to convert it into watt. And it's running for 5 minutes. So 5 multiply 60 to convert from minutes to second. Watt second is the joule. Now we calculated the work of the compressor in joule. To calculate the QL is the amount of heat the compressor is absorbing from the water. It is the same amount of heat lost by the water. Water is cooling 10 degrees, so 5 kilograms of water, C of water multiplied 10 will get you Q lost by water. The COP of this refrigerator, it was required to calculate the COP of this refrigerator is QL divided by work. I am using this refrigerator to cool the water. So the output is QL and the input is the work. Divide the value of QL over work and you will get the COP of the refrigerator. Another example is also a refrigerator. 1 kilogram of chilled water at 0 degrees is placed in a freezer working as Carnot cycle, which is kept at -10, -18 degrees. So the low temperature is -18 degrees. And the room temperature, the atmosphere, is 24 degrees. So TH is 24 degrees Celsius. Find the energy needed to operate the compressor to cool this amount of water to -18. I want to calculate the work of the compressor. It's given also the LM and C water. So now we have a refrigerator working between -18 and 24 degrees. And we are giving this refrigerator amount of work. We want to calculate this amount of work, and this refrigerator is using the Carnot cycle, reverse cycle. The first step, we will calculate the amount of heat the freezer is taking from the water. As mentioned before, this refrigerator or this freezer now will absorb heat from water to cool it down. But it was water at 0 degrees. Now it will be ice at -11. So first of all, we will have M water LM, then M water C ice delta T. This is amount of heat the water loses to get freezed to ice at -18. Now you will substitute with the LM and C water, and delta T is 18, and you get the amount of heat lost by water, which is the amount of heat absorbed by the freezer. And we are talking about Carnot cycle, so QH over QL equals TH over TL. If you want to calculate QH, it's QL multiplied TH over TL. You have QL, substitute with QL here, and you have the high temperature and low temperature, you can get the QH. Now we want to calculate the work operating the compressor. The work operating the compressor is QH minus QL. And of course, all are absolute value, which is 61 kilojoule. The next example is about the second law of thermodynamics and about the entropy. Now we have an isothermal process and we want to prove that the isothermal expansion is a reversible process. To prove this, we will calculate delta S. If the change in entropy of the system and the surroundings will be zero, so this is a reversible process as stated in the second law of thermodynamics. So I will get delta S total of the system and the surroundings. As for the system, which is the gas, the delta S or the change in entropy in case of the isothermal process is nR ln V2 over V1. As for the surroundings are losing heat and gives this heat to the gas. So we will put negative Q, negative because the surrounding is losing heat. Okay, from where I can calculate this heat? The heat the surrounding is losing is the same amount of heat given to the gas. In the case of the isothermal process, heat equals nRT ln V2 over V1. So it will be negative nRT ln V2 over V1 over T, which is nR ln V2 over V1. If you add these two terms, you will have delta S equals 0. That's why we say that the isothermal expansion is a reversible process. Another example on the entropy. Now we have 250 grams of water at 85 degrees and it's cooled down to 20 degrees. So if you draw TQ diagram, you have water initially at 85 degrees and it's cooling down to 20 degrees. We want to calculate the change in entropy of the water. Calculate the change in entropy of the water. We have change of entropy equals integration dq of T over T from initial point to final point. dq equals mc delta T. mc water delta T. Okay? So equals mc is a constant. You take it out of the integration. Integration dt over T, which is ln Tf over T r. Now you substitute with the T final 20 plus 273 to be in Kelvin, and the T initial is 85 plus 273 Kelvin. The mass is 250 grams, so converted into kilograms. This is the C of the water, and this is ln the T final over T initial. After substituting, you can get the change in entropy negative to 10 joule per Kelvin. Of course, water is cooling down, so the entropy is negative because losing heat. The last example we will discuss is about the entropy also. 10 kilograms of water is mixed at 0 degrees, is mixed with 10 kilograms of water at 100 degrees. Find the total change in entropy of the mixture, and it's given the C of the water, the specific heat of the water. So we have 10 kilograms of water at 100 degrees and 10 kilograms at 0 degrees, and they will reach the same T final. They will reach the same T final. The first step is to find this T final. So it is a heat exchange problem. Q lost by the first amount of water equals the Q gained by the second amount of water. M water C water delta T equals M water C water delta T. The same mass, so it's cancelled. Water and water, so C water and C water is cancelled. Delta T water 1. The first amount of water was at 100 degrees and now we reach T final. So it is 100 minus T final. But this amount was at 0 degree and it will reach T final. So it is T final minus 0. After substituting, T final equals 50 degrees. Now we will find the total change in entropy. To find the total change of entropy, we will get the change in entropy for the first amount of water, then the change of entropy for the second amount of water. Delta S1, check this. Delta S1, this is water cooling. So it's MC ln T final over T initial, as we did here. As we did in this when we were having water cooling, it is MC ln T final minus over T initial. So delta S1 for the first amount of water is calculated as follows. As for the second amount, it is calculated like this. So we will calculate the change in entropy, MC water ln T final over T initial 1. And the second one, MC water ln T final over T initial 2. You have the mass of water, you have the C of water, you have the temperatures, you can calculate delta S1 and you calculate delta S2. After substituting, delta S1 is negative, but delta S2 is positive. Let's check if this is correct or not. The first amount will lose energy, so the change in entropy will be negative. The second amount of water will gain energy, so the change in entropy will be positive. Add both to get the total change in entropy, it will be 1050. This was the last example we want to discuss, and thank you for listening.